Chapter 2, Part 4, Mass. Mass is the amount of matter in an object. And we can measure mass on a balance. Weight is how a force affects a mass. And it's typically the effect of the force of gravity on an object. But if something is accelerating a lot, then that can also interfere with the weight because there's different forces on the object. So weight is measured on a scale which measures a force against a spring. Mass is independent of location, but weight is not. A kilogram on Earth is a kilogram on the moon, but the weight changes a lot because the gravity changes. The mass is the standard measurement of the metric system, and the standard unit is the kilogram, because a gram was too small to make a physical object that was accurate for measurements. And so they chose a kilogram because if you look up the platinum iridium cylinder that was held in France, it's still tiny at a kilogram, and so they needed more mass to be able to accurately, confidently make an object of a certain mass, and so that's why they chose kilogram. And so up until about a year ago, we still used a physical object as the ultimate calibrator for this kilogram, but now it's been defined as a constant of the universe. So 1 kilogram is about 2.2015 pounds at a normal Earth gravity. And here we see some subdivisions. A kilogram is 1,000 grams. A decigram is 1/10 of a gram. Centigram is 1/100th of a gram. Milligram is 1,000th of a gram. Microgram is 1/1,000,000th of a gram. A nanogram is 1/1000,000th of a gram. In chemistry, you typically see milligrams. Most chemists work on a scale in which you're measuring out milligrams. So let's convert 343 grams to kilograms. Well, I remember my metric prefixes. A kilo means 1,000. So in 1 kilogram, there would be 1,000 grams. The new unit is kilogram. It goes on top. Old unit is grams. It goes on bottom. And I get 0.343 grams. Or sorry, 0.343 kilograms. How many centigrams are in 0.12 kilograms? Well, I don't know. But I do know that there's 1,000 grams in a kilogram and there's 100 centigrams in a gram. And so I can convert kilograms to grams, remembering that 1,000 grams is the same thing as 1 kilogram. And then I can convert to centigrams, remembering that there are 100 centigrams in a gram. And I get 1.2 times 10 to the 4th centigrams. So again, when you're converting between different prefixes of the metric system, you first convert to the base, so from kilograms just to grams, and then to the new one, to centigrams. And that way, as long as you've just memorized the basic prefixes, you can solve literally every problem. Volume is the amount of space occupied by matter. And the SI unit of volume is the cubic meter, but that's way too big to be useful in chemistry, so we typically use liters or milliliters. And a liter is a cubic decimeter of water at 4 degrees Celsius, or 1/10 of a meter by 1/10 of a meter by 1/10 of a meter. And here we see some tools to measure volumes. Graduated cylinders we use in basic chem labs to make measurements. Volumetric flasks are actually used to make solutions. They only have one calibration marker. We'll get back to that in chapter 14. You can put some chemical in there and then fill it up halfway and shake it up until it's all dissolved, and then fill the liquid up to the marker to make a solution of a specific concentration. Burette and pipettes measure how much of a liquid you're putting into something else. A burette can make many measurements like a graduated cylinder. The pipette just has the one measurement. But basically it's measuring how much of something you're adding to something else. And syringes are used in all research chemistry. In general, in synthetic chemistry and organic chemistry, water and oxygen are terrible for your chemicals and destroy everything. And so you go to great pains to protect them from water and air and the environment. And so syringes and extracting chemicals via syringe and moving chemicals via syringe are common. It's never done in intro chemistry classes just because with needles you always run the risk of getting poked by a needle. And so really that's reserved for research chemistry and graduate school. Because otherwise it's an unnecessary risk at the undergraduate level. Common volume relationships. 1 liter is the exact same thing as 1,000 milliliters, which is the same thing as 1,000 cubic centimeters. Science prefers to say milliliters, Medicine prefers to say cubic centimeters. They mean the same thing. 1 milliliter is a cubic centimeter is 1 cc. And again, just like with meters and yards, we see that liters and quarts are very similar because that's a useful amount of stuff to measure. 1 liter is 1.057 quarts. They're almost the exact same measurement. So let's convert 0.345 liters into milliliters. Well, I remember from my metric prefixes that milli is 1,000th of something. So there are 1,000 milliliters in a liter. A liter divided by liter is 1. I get 345 milliliters. How many milliliters in a cube if all the sides are 13.1 inches each? Well, I first convert inches into centimeters, and I see my cube is 33.3 centimeters by 33.3 centimeters by 33.3 centimeters. So my volume is 3.69 times 10 to the 4th cubic centimeters. And then I remember that 1 cubic centimeter is the exact same thing as a milliliter. And so it's a 1-to-1 conversion. So it's also 3.69 times 10 to the 4th milliliters. Thermal energy. This is a form of energy involving the motion of small particles of matter. And the kinetic energy is 1/2 times mass velocity squared. And so the hotter something is, the faster the molecules are moving. The temperature is the measure of intensity, how hot or cold it is. And heat is the flow of energy. Heat always flows from high to low temperature. If you grab a snowball, it feels cold, because heat is leaving your hand, going down the temperature gradient into the snow, and you have cold receptors in your skin that can sense that, and they start vibrating slower and slower, and that sends a signal to your brain saying you're cold. If you put your hand in boiling water, it'll get really hot because all of a sudden that energy of the boiling water is moving into your hand, and you have heat receptors that start vibrating faster and faster and send information to your brain that something is hot. And the human body has limits on what it can sense for hot and cold. If something is too cold or too hot, it just feels painful. The hot and cold receptors are overloaded, and we just use our pain receptors, the nociceptors, and they send pain signals to the brain. So if you grabbed dry ice or put your hand in a fire, it's just going to hurt because there's so much energy transferring. The human body uses a pain signal to go to the brain, which is supposed to tell you to stop doing what you're doing because you're hurting yourself. The SI unit of temperature is the Kelvin, and this will be really important in Chapter 12 when we use gas laws. The other temperature scales we have are Celsius and Fahrenheit. Celsius was based off of water. 0 Celsius is the freezing point of water, 100 Celsius is the boiling point of water, and then the difference between freezing and boiling point was chopped up into 100 degrees Celsius. Fahrenheit came from a different set of chemicals, ammonium salts, that get really cold. Think of like an instant cold pack for athletes. There's a bag inside of a bag, you squeeze it, you break the internal bag, the two solutions mix and it gets super cold. And that was the type of chemicals that the Fahrenheit system was based off of. And that's why 0 Fahrenheit is so much colder than 0 Celsius, because those chemicals react and get super cold. And then the Kelvin temperature scale, that is based off energy itself. 0 Kelvin means 0 energy, and you can't get less than that because you can't have less energy than 0. And so the Kelvin scale is useful because it's the only temperature scale which is proportional to energy. If you double the Kelvin temperature, you've doubled the energy of the system, and that is not true for Celsius and Fahrenheit. So absolute 0 Kelvin, is negative 273.15 Celsius. It's never been achieved, but I think they've gotten down to 0.15 Kelvin or so. It's almost been achieved. It might be a theoretical limit because it's hard to isolate a system from the rest of the universe so that energy doesn't slowly leak in. To convert, Kelvin is degrees Celsius plus 273.15. Likewise, we can go the other way. Degrees Celsius then would be Kelvin minus 273.15. Fahrenheit is 9/5 Celsius plus 32. Or to go the other way, Celsius equals 5/9 times Fahrenheit minus 32. And that would be in parentheses. So these are the temperature conversions that you will use in this classroom. We convert 723 Celsius to Kelvin. We add 273.15 to get 996 Kelvin. We convert to Fahrenheit. We take 9/5 times the Celsius temperature plus 32 to get 1,333 degrees Fahrenheit. The Celsius and the Fahrenheit systems cross over at -40. And so that's the one place they're the same. -40 Celsius equals -40 Fahrenheit. So what is the temperature of body temp, 98.6 Fahrenheit, when we convert to Celsius? Well, we take 9/5 times, or we are solving for Celsius. So if we go back and look at our formula, we will take degrees Fahrenheit minus 32 times 5/9. So here we have degrees Fahrenheit minus 32, and then times it by 5/9, and we get 37 degrees Celsius. Density. This is mass divided by volume. How much mass is there per unit volume? It's a physical property of a substance. Solids and liquids are expressed in grams per milliliter. Gases are so much less dense that they are expressed as grams per liter, because that allows you to use convenient numbers and not always be writing 0.000 something. And so that's why gases get a different unit. You must always write the temperature of a density because volume changes with temperature. If you change the volume, you change the density. So whereas water has a density of 1 gram per milliliter at 4 degrees Celsius, that density is down to 0.97 grams per milliliter at 80 degrees Celsius. Density changes with temperature. A specific gravity is just like a density, but you're comparing a density to something else. But you're almost always comparing it to water at 4 degrees Celsius. And so basically, specific gravities typically have the same number of a density, just no units. Because it's a comparison, it's a ratio. How dense is it compared to water at 4 degrees Celsius, which is 1 gram per milliliter. To solve density problems, we have a useful triangle we draw. We got the mass on top, density, and the volume. If you want to solve for density, cover up density. It's mass divided by volume. You want to solve for mass, cover up mass, density times volume. You want to solve for volume, cover up volume. It's mass divided by density. So this triangle will always tell you which formula to use. Here we want to solve for density, so we cover up density, mass divided by volume. Oops. And we get 6.09 grams per milliliter. The density of gold is 19.3 grams per milliliter. What is the volume? Let's go back to our triangle. We're solving for volume. We cover up volume. It's mass divided by density. So we take the mass and then we divide it by the density, and we get 1.3 milliliters. What is the mass of 1.5 milliliters of ethyl alcohol? We come back here to our triangle, cover up mass because we're solving for mass. It's density times volume. So we take the density, or the volume, times the density. Or you can do density times volume. Same answer. And you get 1.18 grams. And that is the end of Chapter 2.